In 1738, Euler observed that no cube plus 1, even allowing fractions, can be a square, except when the cube is 8. That is, 2 cubed plus 1 equals 3 squared is the only non-trivial solution in integers. Euler supported this result with an argument by infinite descent. In this presentation, we'll approach the same problem from a different direction. We'll present a fresh elementary proof, relying only on classical tools. No algebraic number theory, no quadratic integer rings. Just a careful use of factorization, coprimality, parity, and classical parametrization. In other words, standard tools from elementary number theory. We first factor x cubed plus 1 and examine whether the two factors are coprime. Observe that the square of the first factor minus the second one equals 3x. Since x and x plus 1 are coprime, it follows that the greatest common divisor of the factors can only be 1 or 3. The problem therefore splits into two cases according to this greatest common divisor. We then analyze each case according to parity, noting that x and y have opposite parity. Case 1 deals with the greatest common divisor equal to 1. Set the first factor equals to a squared and the second factor equal to b squared. We may assume a and b bigger than 0 without loss of generality. Substituting x into the second equation and simplifying gives a raised to the fourth minus 3 times a squared plus 3 equals b squared. Subcase x even and y odd. Then a and b are odd, viewing this equation as a quadratic in a squared, and completing the square, we got a square equals a square minus 3. Hence, 3 can be factored as 2a squared plus 2b minus 3 times minus 2a squared plus 2b plus 3. Since the first factor is bigger than 0, as a and b are bigger than 0, and the product is positive, both factors must be positive. Thus, one factor equals 3 and the other 1. If the first factor equals 3 and the second 1, then b equals 1 and a squared equals 2, hence no integer solution. If the first factor equals 1 and the second 3, then b and a equals 1. Thus, x equals 0 and the trivial solution. Had we not assumed a and b bigger than 0, we would also have to consider the case where both factors are negative. If the first factor equals minus 3 and the second minus 1, then b equals minus 1 and a equals 1. Thus, x equals 0 and the trivial solution follows. If the first factor equals minus 1 and the second minus 3, then b equals minus 1 and a squared equals 2. Hence, no integer solution. Thus, the negative cases merely mirror the positive ones already discussed. Subcase x odd and y even. Hence, a is even and b is odd. Write a as 2u and b as 2v plus 1. Substitution into the equation yields 4u squared times 4u squared minus 3 plus 3 on the left-hand side, while b squared equals 4v times v plus 1 plus 1. Comparing both expressions gives an equation of a form 4a plus 2 equals 4b, thus forcing 4 to divide 2, which is impossible. Hence, no integer solution arises in this subcase. Case 2. The greatest common divisor is 3. Set the first factor as 3a squared and the second one as 3b squared. Since x times x minus 1 is always even, it follows that b is odd. Substituting x into the second equation and simplifying gives 3a raised to the fourth minus 3a squared plus 1 equals b squared. We first rearrange and then square both sides. We can rewrite the left-hand side as a difference of squares. Therefore, we arrive at a Pythagorean triple. We can now apply the classical parametrization of non-primitive Pythagorean triples, with the hypotenuse equals w times u squared plus v squared, one leg w times u squared minus v squared, and the other leg W times 2uv, with u and v coprime of opposite parity and w absorbing all common factors. Note that 3a squared divides the three terms. Moreover, all three quantities are even, so w must absorb a factor of 2. Hence, 6a squared divides w. Let w equals 6a squared times w sub 1. There are two possible parametrizations to consider. Parametrization 1, the hypotenuse equals 3a squared times a squared plus 1. The first leg, w times u squared minus v squared equals v squared minus 1. And the second leg, w times 2 times u times v equals 6a squared. Since 6a squared divides w, this forces 2 times u times v times w sub 1 to be equal to 1, which is impossible since u, v, and w sub 1 are integers. So this subcase is discarded. Parametrization 2, with the same hypotenuse, one leg w times u squared minus v squared equals 6a squared, and the other leg w times 2uv equals b squared minus 1. Again, since 6a squared divides w, this forces w sub 1 times u squared minus v squared to be equal to 1, which can only happen if w sub 1 equals 1, u equals 1, and v equals 0. Then b squared minus 1 equals 0, so b equals plus minus 1. Hence, x squared minus x plus 1 equals 3 factors as x plus 1 times x minus 2 equals 0, giving x equals minus 1 or x equals 2. This yields the trivial solution and the only non-trivial solution. 2 cubed plus 1 equals 3 squared.
That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.